Okay, so today I'm using my computer to record this uh lecture. So okay, so let me go here. So okay, so last time we are left to show that uh so yeah, remember last time we just used a homomorphism, right? So uh yeah, so we are doing a injective homomorphism from uh Z to uh the Dex transformation group of gamma. So actually then we show that it's also surjective. So therefore it is also a bijection. Okay. So um actually why is a homomorphism? Because if you say if you have m plus n, then did you do a combination? Yeah, so you do a combination, we map it to like the uh yeah, so basically if you give it this math a name, maybe let's call it chi or something. So if you have this chi, so chi of like m plus n, which is exactly phi of n. So phi zero of then phi m plus n, then you exactly just child child app, right? On the condition, but for the uh for um okay, yeah, okay, all right. So yeah, so this implies that um so thus we have the child one of C star, which is isomorphic to the subject transformation groups gamma, which is isomorphic to Z. Yeah, so yeah, remember like in the section of the Dutch transformation group, actually we show that the fundamental group of the uh, what we should, fundamental group of the target space uh, can be bijectively identified with the Dutch transformation group, and then this C is like the Dutch transformation group under this homomorphism. Okay, and then so okay, so in fact. Uh, okay, so since the lifting uh gamma tilde of sorry uh small gamma tilde of gamma satisfies the relation that small gamma tilde at zero is equal to V naught and small gamma of one is equal to z naught plus one, which is equal to five log of z naught. Okay. Uh, okay. So here, remember that uh, we have defined the identification of the fundamental group, and together with the uh, elements of the dash transformation group, right? So basically, uh, oh shoot. Uh, okay. So here we have a gamma, sorry, small r, small gamma, and then we have the lifting that uh it lifts to the naught. So uh okay. Yeah, so there is a special um y equals to z naught plus one. Uh so lifting wait, what is this small gamma? Oh, okay. So this small gamma is exactly given by mm, okay. Yeah, so remember that this small gamma, yeah, so we have defined last time that uh yeah, so if you have the initial point, let's say z naught, we define the gamma, the little gamma 2 then to be the point that you start at the z naught, and then it goes to z naught plus one. So this is like the gamma 2. And then so this is the exponential mass. And then so here you have the theta naught, which is the image of the naught. Okay, so and then we define like the yeah, so since so the image of this gamma tilde under the exponential map is exactly uh the incomplete circle around the zeta naught. Okay. That hit the zeta naught. Okay. So this is like the gamma. The small gamma, the yeah, the little gamma. Okay. And by the unique lifting, there is a unique yeah up to the okay. Yeah, up to the base point here. So okay. Uh, okay. Oh, sorry. Yeah. Okay. So now, okay. So yeah, I thought, so for the identification of the pi one and also the direct translation rule. So, oh, yeah. Yeah, sorry. Um, okay, so um, okay, so in the current space, sorry, in the uh, so in the theorem, in the first theorem that we proved about the deck transformation, okay, so actually, um, so there is an identification between the pi one and the deck transformation group, right? So the theorem states that if you have a point x in the x tilde current space, okay, and then you have the uh, little gamma tilde as a path from x naught tilde to x. Okay. So x naught tilde is like the fibers, one of the fibers. Okay. So like this is the projection capital gamma. And then we have the let's see so here this is the base point x naught. So this gamma tilde is a path. Oh, okay. Joining this x tilde and the x. Oh, um, okay, yeah, I joined these 2 points. Okay, and then um, let me so, um, so and then you let okay, so yeah, so x naught is the base point at the space x. Okay, yeah, and then we pick an element. Okay, element alpha that belongs to pi one x x naught. Okay, so a homotopy class represented by the alpha. Okay, in yeah, okay. And then alpha tilde is the unique lifting of alpha to a path in x tilde with the initial point x naught tilde. Okay, so there is a unique list. Okay, let's say alpha tilde. Okay, and then yeah, so gamma tilde one is okay. So then you do the projection of this point of this path, right? Projection of this path. Okay, so let's call this path little r here. And then okay, so then there's a unique lifting of this path. Let's call this little gamma 1 to the. Okay, which is the lifting of this little gamma. Okay, okay. So then with the initial point, uh yeah, so this is the initial point, which is this the end point of this path. Okay. Okay, so and then okay, so then this point, so okay, so okay, so this alpha, for each element, okay, so for each element of this alpha uh represented by the for each element in type one, okay, uh the corresponding, yes, so the corresponding, wait, uh unique lift. Why the lift? Why it guarantees the same if you have a total? Okay, okay. So yeah, yeah. I think by the homotopy lifting, you will have the uniqueness of the, because if you have a homotopy uh downstairs, that give you a homotopy upstairs. So actually, you by the homotopy lifting theorem, something these are homotopic. Therefore, the family of the lifting, wait, shoot. Yeah, so this x is always fixed, right? Yeah, so this endpoint, since they are homotopic, uh, oh yeah, so this alpha, yeah, so this alpha one will always be fixed. So what am I saying? So does this depends on, does this lifting depends on this one? Uh, yeah, I don't see any reason. Let me see. Yeah, so if you do the projection downstairs, uh yeah, suppose you have another path, right? So why would you do the projection to get another, yeah, uh get another, oh, y get the same endpoint with different. Oh shoot! Because it's executed is a universal covering space. Okay. Okay. I think that makes sense. Okay. Because it's a universal covering space. Therefore, these two maps they are exactly homotopy to each other. Okay. And then therefore, yeah, so therefore this shows that the endpoint is wait, what was yeah, so these are homotopic, right? So yeah, so then you do the projection. You do a projection downstairs. So will it still be a homotopic? You have a homotopy from yeah, yeah, these are also home you do yes. It's continuous map. Yes. Okay. Okay. Yeah. By the homotopy lifting field. Yes. Okay. So at the endpoint, I'm start. Uh, yes. But here, did you? Okay. 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 So okay. So yeah. So for each element, right? So there is a unique associated phi that maps any point to this point. Okay, here this path is going by that. Okay, so now let's see. So since the lifting of this little gamma theta of gamma satisfies the condition that um, I have the little gamma of zero is equal to z naught. Okay. 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 So think about this part of the z naught. Okay. So think about this part of the z naught. And then, uh, okay, okay. Maybe I'm thinking too much about this one. Okay. Uh, yeah. So let me yes. Let me right. Let me continue here. So, um, so okay. So yeah, continue from here. So we have pi one of c star zeta log is the infinite secret group uh generated by uh this little gamma, the functional group, the whole the yeah homotopy class of the homotopy equivalence class generated by the little gamma function at the yeah zero naught. Okay, So that is, yeah, so, um, okay. Yeah, I think I'll just stop on here. Okay. So, let me quickly think why this is a infinite sequence group. Um, okay, let me divide this. Okay, so we just defined the identification the um of this element. Okay, any element in the pi one of uh x naught. Okay, and then for that element, so basically what you do is that this element give rise to a okay element in the deck transformation that maps with x to the endpoint, right? To the endpoint little gamma one tilde, yeah, of this x. Okay, so yes, this is the map here. Okay, so 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 here we are saying that this group, right? This group is an infinite secret group generated by why is that? Um, um, so okay, so mm, the lifting little gamma tilde of gamma satisfies the little gamma tilde at zero. Okay, little gamma tilde at zero is equal to z naught. Okay, we do have that. Okay. One is equal to okay then. Oh shoot. Okay, I know. Okay, with a system group generated by. Okay, so I know that there is an identification between this and the test transition group, right? Yes. So okay, yeah. So the identification is given by okay. So if you pick any element, so any element. Wait, wait. Why this little gamma is the final? It doesn't. Yeah, it's not. Uh oh. Okay. So yeah. So because here it really hits the endpoint, right? For this little gamma tilde. So therefore, I think this gamma is actually contained, actually hits this point. Okay. Um. Okay. So for any element that is inside this fundamental group, okay. So let's think about that as let's use the letter here, alpha. So that at the uh So for any alpha, we have that what is the corresponding maps? So, okay, so wait a second. Okay, so what you have is you have the lifting of this alpha. Okay, okay. Um, which is this one. Oh, shoot. Okay, so let's say y, this part one of this yeah. So let's say y is part one of yeah. Okay, okay, okay. Yeah. So this is just that. Okay. So this is yeah. So we show that this is actually a element of the fundamental proof, right? Yes. Okay. Okay. So and then okay. So let's see why this is okay. So it's generally by that. Okay. Okay. Um. All right. Let's continue next time. Okay. So next time I will show why this part one of C star theta naught is the infinite cyclic group generated by this element.